First of all, I'd like to thank the organizers for inviting me to this nice webinar conference, and I'll present recent results and new developments using the INGA facility.
I was. Hello. Okay. Yeah. Hello. Okay.
Yeah. Yeah. So this is the INGA collaboration, and a lot of young students and researchers are involved in these experiments, and I'll be presenting some of the results. So I'll give you an overview of INGA, then I'll talk about the ancillary detectors, then selected results, and then summary. So Nico told me that there are a lot of students who are attending this conference. So for them, I would like to say that there is a very nice article on large gamma array and the scope of nuclear spectroscopy. And you can see a lot of arrays which are there, which are present for, which are used for nuclear structure and reaction dynamic studies with stable as well as radioactive ion beams. So INGA started in 2001, and it moves in between the three accelerator centers within India. In Bombay and then in IUAC, we have in Delhi, we have Pelletron and LINAC accelerators, and then we have in VCC, we have cyclotron, and it moves between the centers and spends 1 to 2 years, but now there are scope of doing parallel campaigns in the three centers. So one of the aspect of the full array started in around 2008, where the full electronics was developed in-house at IUAC with analog electronics and ADCs, and the power supplies and everything was developed. And then it moved to Mumbai, where we included the digital XIA-based data acquisition system, and that gave higher stability and high counting rate. And now in VCC, the INGA is running with around 12 detectors with digital data acquisition system, and many experiments have been performed. So this is right now we have the array, and because we have less number of experiments, we are now trying to develop ancillary detectors like cesium hydrate, silicon, and lanthanum bromide detectors to augment the selectivity of this detector system. So the array has like 24 clovers and 24 BGO detectors. To handle this, we have 100 megahertz 12-bit ADCs, and the data acquisition system is highly versatile to take care of complex trigger systems. It can handle high count rate, it has high gain stability, and we can run the system with triggerless mode as well as with trigger, and then we can also do measurements using prompt delayed coincidence and study long-lived isomers. What you can see here is that the count rate with increasing count rate, there is slight reduction in the energy resolution, and in principle, one can go to very high count rate, which is not possible with the analog electronics. This is the time window which we use for our coincidence measurement, and this is a detailed simulation of the INGA has been carried out with GAN4, and you can see here this is the black one is your simulation, and the red one is the measurement, and they are normalized, of course, but they are nicely matching. And this is with BGO, without BGO shield, and this is with BGO shield, and this is with add back spectrum. So this is the relative efficiency of the clover, and this is the green one is the simulation, and the dot and the field points are the actual data. And the relative efficiency is also nicely reproduced in the simulation, and the add back factor for the clover is also nicely reproduced. Here you can see the 4 crystals in the cryostat, and then the BGO crystal, which is the BGO sealed for anti-quantum suppression. So I will try to talk of 4 experimental results. 3 of them are with ancillary detectors, and 2 are using Doppler shift as attenuation method. We have measured the lifetime of excited states. So first I'll talk of reaction dynamics with weakly bound nuclei. So this experiment was done to study the fragment capture reaction mechanisms with 7 lithium on 93 niobium. And inside the target chamber, we put telescopes, silicon telescopes, and this is the particle spectrum, delta E and E spectrum. And you can nicely separate the alpha and the proton in this. And this was one of the first experiment where we included the ancillary detector in the array, and we could combine the silicon signals with the germanium and BGOs, and we did the coincidence measurement. So here you can see the alpha gated gamma spectra, and which are mainly then the tritium capture and then production evaporation channels of molybdenum and 94, 96, 95, and 94. And similarly, we have also the zirconium and niobium channels are also seen. Then we see that the maximum alpha production in this is coming from the tritium capture, and then around 10 to 20% is from the compound nucleus evaporation, and then there are direct breakups which are less. So main summary is that tritium capture is a very dominant channel for alpha production in this lithium 7 induced reactions. So then there is also a plan to make a cesium hydrate array for particle tagging for high-spin spectroscopy and nuclear reaction studies. So in one test experiment, we have this 13 carbon on 82 selenium at 60 MeV. This experiment was done. And here using the digital pulse processing, we could look for the difference between the cesium like gamma in pin diode, the alpha signals and protons, and gamma in the cesium iodide. And this is the typical particle ID spectrum. You can see the cesium iodide is kept inside the target chamber. And then we could successfully do the alpha gating to look for the strontium, and then proton gating to look for the yttrium channels. This is the total projections, and you can see that these are very weak. The alpha gated peaks are very weak. But on the other hand, and you can see them very nicely in the like alpha gated spectrum. You can see the strontium channels much stronger and cleaner compared to the total projection. Similarly, the proton gated spectrum also shows very nicely the yttrium channels. So one experiment was done by the SINP group to look for the nuclear level density from gamma gated evaporation particle spectra. So this is the compound nucleus, and then the compound nucleus decays by particles like charged particles and neutrons, and then the gammas are emitted. By measuring the charged particle spectrum in coincidence with the gamma rays, the idea was to measure the level density of some of these isotopes. So this reaction was 9 beryllium on 64 nickel, and then we have 15% channel is 68 zinc, and the alpha. This is the energy spectrum of the gamma with the alpha energy of the alpha, and this is the gamma spectrum, and we have put gate on like in coincidence with the 332 and 1152, which 152 keV transitions, which is 68 zinc. We try to look for the alpha spectrum, which is shown here. One of the thing is these are 8 minus state and 6 minus states, which are decaying by these transitions, and these are negative parity states, and they are coming from the compound nuclear decay, and because the even spin and odd parity can only be populated through this reaction. So this is the 68 zinc level scheme. This is the alpha spectrum, which was fitted with the statistical model, and the level density parameters were extracted, and they are used for calculating the N gamma cross sections for 68 zinc. So then there's another work which is the lifetime measurements for 2+ states in 112 and 120 tin by Doppler shift attenuation method. So this is there is a lot of interest in the tin isotopes because of there is a challenge to understand the evolution of collectivity of 2+ states along the chain of tin isotopes. And there is a lot of scattering of data, and because of which there is a program which started to look for the 2+ states lifetime using Doppler shift attenuation method. So the technique which has been used is inelastic scattering, which is different than the other methods which have been used till now. So use 32 sulfur at 120 MeV on 120 tin. Another reaction, this was below barrier, and then another reaction was done with 35 chlorine on 112 tin at above barrier. And in this case, the velocity profiles of the recoiling nuclei through the target and backing combinations are calculated with inputs from the reaction kinematics and angular distribution of the scattering cross sections using Fresco. And the stopping power and the trajectory simulations were done with SRIM. And then these trajectories were fitted with the used for the Doppler shape calculations using this line shape. So this is the result for 120 tin. You can see that this is 90 degree, 115 degree, and 140 and 157 degree. And this is in this method we got the lifetime. This is the work here, and which is slightly smaller than the values which are reported before. And effect of feeder states found to be inconsequential owing to the below barrier bombarding energy. And based on that, we got this the B2 value, which is like 0.215 p square v square. Now, in the another experiment where we used much higher energy, because of the higher energy, we could populate the 3- state, and by using the 3- state to 2- state as a gating transitions, we could extract the line shape of the 2+2 and 0+. And here we find out that the lifetime of the state is though it is matching with NN prime method, but there is some disagreement with the previous measurement of DSM. And the B2 value extracted is around 0.229, which is compared with the cell model calculations as well as the other isotopes. So here you can see this is the mass number with the BT value and the different like BT values from different measurements have been plotted here. And you can see that the red ones here is the cross and star here are the our measurement, and they are compared with the generalized seniority model as well as the Monte Carlo cell model, which was reported in 2018 by Togasis and et al. So we find out that the Monte Carlo cell model agrees well with the measurement of 112 tin in this case. To find out more about this, we looked into the T plot, and the calculations were done by Togasis and Shimizu-san. And they looked for the, you can see here that both 0 plus and 2 plus have oblate shapes in the T plot. And this is happening because there is a strong proton core excitation from G9 half orbital to D5 half. And then the neutron deformation is enhanced by the proton-neutron interaction, and because of which the 0 plus and 2 plus of 112 tin are oblate, and because of the similar shape, there is an enhancement in the B2. And if you see here, the 112 tin and 110 tin, they have large B2 compared to any other isotopes of tin. So it is essential that we try to do more measurements to confirm this part. So now I will come to the third topic of octopole structure, and I will mainly talk about octopole correlations in mass 80 region and mass 140 region. So this experiment was done at TFR using 9 beryllium beam on 76 germanium. You can see that a positive parity and a negative parity bands have been populated in 79 selenium. And you can find out that there are a lot of parity changing transitions which have been established. So line shapes of some of these transitions have been extracted, and using a Doppler shift attenuation method. And from there, you can extract the lifetime of the states. And from the lifetime, we have extracted the V1 values and V2 values, and the ratio of the V1 by V2 are compared with the thorium 78 bromine, 125 barium, 79 selenium, and 144 barium. It indicates that this is the values here, V1 by V2, which is closer to the barium isotope, 125 barium. And we then try to look for the absolute V1 values. But before that, we looked for the aligned angular momentum between these two bands, band 1 and band 2. And we find out that there is a difference in aligned angular momentum over the entire spin region of the bands, indicating octopole correlations is present in 79 selenium. Then we, from the V1 values, extracted V1 value, we extracted the electric dipole moment, and these are the values for 228 thorium, which was recently reported in 2020 this year. And some of the lower spin states, we find out that the values are matching. There is a slight overlap with that of thorium 228. And that says that the electric dipole moments are large for 79 selenium, and more investigations are required to understand this enhancement. Then reflection asymmetry particle rotor model calculations have been carried out by a Meng's group and we find this says that the nuclei are very soft in beta 30, and you can see using this potential, which is calculated using the CDFT in 3D lattice calculations, the potential energy surface. The particle rotor model has been used to calculate the energies, and they are nicely reproduced for these two bands. One is neutron in G9 the other one is neutron is F5 and the B2 values and BM1 values are also nicely, the trend is nicely explained. However, in case of B1 value, we find out that the B1 values are slightly, calculated values are slightly lower compared to the experimental data, and that says that additional informations and measurements or additional theoretical investigations are required to understand the shape, the enhanced octopole correlation in 79 selenium. So to study the in mass 140 region, we find out the lifetimes are little longer, and we need to use different techniques. So for that, recently we have started working on the lanthanum bromide detector array. And within the array, we can couple around 18 lanthanum bromide detectors. And this is the simulation which was done and compared with the germanium detector, the clover crystal. And you can find out that the simulation is nicely matching. So each of these lanthanum bromide detector are 2-inch by 2-inch size, and the efficiency will be almost equivalent to that of the clover, which is kept at 25 centimeter, where the lanthanum bromide is kept at around 13 centimeter. The compared to the germanium detector, the lanthanum bromide detectors are fast, and then we have to use different type of digitizers for that. So we have now coupled a 250 megahertz digitizer for lanthanum bromide in a different crate with 100 megahertz digitizers for the clover and the cesium hydrate. And the synchronization between these two things has been done. You can then we had to optimize, and the 2-crate synchronization has been carried out recently, and this is the result from the experiment. So as you can see that the energy and time resolution has been compared here. The energy resolution in germanium detector is much better for compared to the lanthanum bromide detector, while the timing resolution in lanthanum bromide detector is whatever we have achieved is around 450 picosecond. And using that, we have measured the lifetime of 125 tellurium 9-half states. And this value is around 680 picosecond, which is matching with the literature value. So then we looked for the particle core coupling, because there is an interesting aspect that how particles are coupled with the octopole vibrations of the core. So we looked into these barium isotopes, which is an interesting thing in the literature, that there is some of the large B3 has been reported in neutron-rich barium isotopes. And it will be interesting to see that how the proton particle, when it couples with these bariums, how there is a transition, like how the B3 strength evolves. So these are the data points for 129 lanthanum, 133 lanthanum, and the upper limit was given for 137 lanthanum, and this data was rather old, almost 30 years old. So we tried to do this measurement using the lanthanum bromide and clover array. So this is 169 keV. This is the spectrum, the level structure of 137 lanthanum. It's a 11.5 minus state, which is decaying by 170 keV. And there are this 994, which goes directly to 5 plus. So this is the interesting transition for which we are interested to extract the B3. And we measured the lifetime. We got the lifetime. This is the lifetime of the 11.5 state. We find out the lifetime is around 270 picosecond. And this lifetime is smaller than whatever has been reported almost 50 years back, which was like 410 picosecond. So then
you was in your questions.
Sorry?
Still 5 minutes left.
Yeah.
You are within your 5 minutes of questions.
Yeah.
Wrap up.
Yeah.
Okay. Thank you.
Yeah. So then the B3 values of, we find out that the B3 value, whatever we got, is around 22, around 23 Weisskopf unit, which is very close to the B3 value in case of 136 barium. But there is theoretical understanding has to be, we need to understand that how in case of lanthanum isotopes, the B3, there is a sharp rise. How is it happening? We are trying to find out that, and more theoretical investigations are required to understand this sudden enhancement of B3 in lanthanum isotopes around n equal to 80. So this brings me to the summary of the talk. I talked about the use of ancillary detectors, mainly the silicon detectors, cesium hydrate detectors, and lanthanum bromide detectors, which will broaden the scope of the studies, which is possible with the INGA. And I talked about some of these results. And in future, we'll try to do more measurements in the lanthanum isotopes and barium isotopes and try to find out why is the enhancement and in the B3 in case of around n equal to 80. Thank you for your attention.
Thank you. Can we just thank the speaker? Okay, there's some time for questions. There are 2 questions on the chat room. So the first question asks if you could please show the plot of the B2 values in the tin. And it says he doesn't see the data point in tin 112 compared to other B2 values.
Yeah, give me a minute. Yeah, can you see now?
Which one? Yeah, the square is your data point, no? Which one is your data point?
These two. The red, this is
oh,
for
this
the,
one. Okay.
Yeah, so this is here and 112 tin is here.
Yeah. And the June clouds data is down there. Yeah, I see.
Yeah.
So now you have full agreement. Yeah, this was a very nice measurement because lifetimes are always difficult. Yeah. And another question I have: how do you account for the feeding from high lying states?
Okay, so what we have done in case of 112 tin, we have used higher beam energy, and because of which we could get on the 3 minus to 2 minus state. We could get on that, and this is like lifetime fitting with above, get it from above, and from there we could extract the line shape of 2 to 0, and that's how we can take care of the feeding in case of 120. And in case of 120 tin, the beam energy was below barrier, and we try to look for the feeding, and we find out that it doesn't have substantial contribution.
Okay, thank you so much.
Here's one more question. How many lanthanum bromides were used to get the full width half maximum at 1.5 nanoseconds for time resolution? And can you also comment on the beryllium 78, which is also shown in the ratio plot of EM strengths.
Yeah, so in case of like you're talking of this plot here.
Yes.
That's correct.
Yeah. So this is between the two detectors, which was like a standalone two detectors were used to find out the timing. And then we tried to do the measurement with, so this is with the in-beam measurement with a similar time with a prompt transition combination with similar energy, we find out this. And this is with 14 lanthanum bromide detectors.
Okay. So the other one was 78 bromine. You showed this also in your plot of electromagnetic strengths, you see. So I was just wondering.
70, yeah,
8 bromine. I was wondering whether you can comment on that case as well for octopole correlations.
See, these are from the intensity measurements, intensity ratio measurements. So they are comparable to 79 selenium.
Okay.
So they have similar gamma beta 3 softness as 79 selenium.
Okay, there's another question, but I think we need to move on to the next speaker. I think that's something you guys can discuss, directly among each other. Right, thank you very much for a lovely presentation. We'll move on to the next speaker. It will be